Just going to do another one of the curvature ones. There are two formulas. That's my go-to one, so that's what I'm going to do. We're being asked to find the curvature at a particular point. We'll worry about the point after we've got this guy. So find the first derivative. Well, that's a power rule, so you get 8t. That is 1 over t, and that's actually a product rule. So if you call this f and g, you get f dashed g plus f of g dashed. So what does that look like? It looks like 8t, 1 over t, and a log t plus 1. Okay. That look okay? Differentiate, differentiate, product rule. Then we'll do the second derivative. And the second derivative is 8, negative 1 over t squared, and 1 over t. And what should we do? We'll do a cross product. So it's going to be I j. Okay. And an 8t, a 1 over t, and a natural log of t plus 1, and an 8, and a negative 1 over t squared, and a 1 over t. And then I'm going to pause. If the question had been find kappa of t, I would have had to have done this, right? Because the answer would have t's in it. But I just thought that I can make my life a little bit easier. I mean, I could do a cross product. Now, it's not that I couldn't. It would be a bit messy and a bit long, and I'm seeing if I can avoid that. Since they're only interested in the curvature at one point, all I need to do is find out what number t is, right? And I can plug it in here, in which case I can do it with numbers, right? Which is a lot easier than to do it with variables. So this space curve at 4, 0, 0, what t value gets you that guy?
1 t.
1.
Agreed. You want to tell people where you got that from? That's the right answer.
The only thing to get 4 for 4t squared is 1.
Well, you could have got negative 1. Right, 4 negative 1 squared would also work. So at least you know it's 1 or negative 1, but why is it 1? I would have chosen a different guy to do the matcher.
Natural log of 1 is 0.
Yeah, you see that one there, the middle one? Right. That one was good, but all that did is it gave you two choices. You then had to figure out which one it was. So that means that the cross product I'm going to do is only going to be at t equals 1. So I have an I have a j, and I have a k. And that's 8 times 1, 1 over 1. The log of 1 plus 1 is 0 plus 1 is 1. That's 8, that's negative 1, and that's 1. Would you agree that's just much easier to deal with? And continuing then. It's going to be so many i's, take away so many j's, plus so many k's. Right, if I cover this up, I get 1, take away negative 1 is 2. The middle one, I get 8, take away 8, which is 0. And the end one, I get negative 8, take away another 8 is negative 16. And so this guy becomes 2, 0, negative 16. Now, according to my formula, I need to find the magnitude of this cross product. So that's what I'm going to do now. Which is going to be 2 squared, 0 squared, and negative 16 squared. And oh god, 196. Oh, 200, which is 10 root 2. I wasn't expecting that. Okay, I need that number. According to our formula, I also need to know the magnitude of the first derivative at 1 and then cube it. So what's that going to be? Magnitude of that guy is the magnitude of 8, 1, 1. And the magnitude of that vector would be 8 squared, 1 squared, 1 squared, which is the square root of 66. So the curvature at 1 is the magnitude of the cross product divided by the magnitude of the first derivative cubed. So in this case, it's 10 root 2 over the square root of 66 cubed. Oh, God in Himmel. I want this thing to look vaguely pretty. Well, anything I can do to this fella.
Professor,
Yes.
Nathan wrote in the chat that 16 squared is 256.
Nathan is a pain in the butt, but he's also correct. Thank you, Nathan. So, square root of 260 over the square root of 66 cubed. Now, what on earth does let's see what the answer looks like so I know where I'm heading. Okay. According to what we have in front of us here, that this fella at the top ends up being 2 square root of 65. And this guy in the bottom ends up being 66 square root of 66. That partially cancels. And you get that. I guess you could rationalize the denominator by doing that. And if you do that, you get 2178. And on the bottom, a ridiculously big square root. And I'm not impressed by that answer. I mean, it's just ugly. I guess there comes a point in time where you probably should just turn the thing into a decimal, but since we don't want decimals, we have to fight our way through that one. Right, let's try and convince you that that guy is 2 root 65. Well, it must be because 4 times 65 gets you 260. So that's why that works. Let's convince you why that is that. If you take the square root of 66 times the square root of 66 times the square root of 66, don't those two guys get you the 66? So that's where that came from. If you rationalize the denominator, multiplying those two ugly guys together is this number, and those two become a 66, and 33 times 66 is where that number comes from. Not a pretty answer. I like it much nicer, don't you, when the answer's 2? You know, they design it in such a way that you get a really pretty answer. But it is the curvature, and so it's the answer. Any questions about curvature before we move on? Are you comfortable with they take time, but you just follow the procedure and you should be fine. Yeah. Let's leave that one and move on to our next topic. Which is 13.4. Motion in space. We've kind of touched on this already. Imagine I have a space curve traveling in 3D space, and it looks like this guy, right? We know how to find its derivative. Let's give it some values then. Suppose r of t was t squared e to the t 2t, just for argument's sake. Its derivative would be 2t e to the t 2. Agreed? Now, if something is moving, right, motion in 3D space, that first derivative, can we pretend that it happens to be here, right? Isn't the derivative a vector that tells you the direction that you shoot off to your death in the roller coaster, right? And this fella has another name. He is called the velocity vector. Seem reasonable? Right. Analogy. Can you remember Calc 1 when you did the position of a function? It was called S of t, right? And it was, you know, something like that, right? And wasn't the velocity the first derivative? You remember doing that? There are many meanings to what a derivative means, right? It's all to do with context. One of the meanings for derivatives is its rate of change. So this is rate of change of position with time. So it's velocity. If you find the second derivative, in this case, differentiate that, you get 2. Differentiate that, you get e to the t. Differentiate that, you get 0. You also get a vector. Now, if the first derivative is called the velocity vector, what name do you think the second derivative is going to be called?
Would it be acceleration?
And it is. Would it make sense that something is traveling in 3D space, that it would have a velocity and an acceleration? The weirder thing is it's not a number, right? Like 42 or -8, right? It's a vector. But when you move in 3D space, that's what you get. And the velocity vector here is, sorry, the acceleration vector here is called a of t. And couldn't you also describe it as the derivative of the velocity vector as well? Isn't the derivative of this guy the same thing as the second derivative? So the rate of change of velocity is acceleration. Now, back to shooting off to your death. First derivative, this red vector, right? This vector could be a short vector or a really long vector. The length of that vector, its magnitude, is your speed. So the speed at which you are shooting off that roller coaster is the magnitude of the first derivative. It's the magnitude of your velocity vector. Now that is a number, we call them scalars, right? That is a scalar. So you could be shooting off to your death at 400 miles an hour or at 40 miles an hour, right? But it's a number, right? So speed is a number, velocity is a vector, right? Distinguish those two ideas in your head, right? Speed is a number, but velocity is a vector. We tend to use those two words in everyday language interchangeably, right? Because, you know, cars tend to drive in a 2D world, aren't they? right? We don't have flying cars yet, right? So somebody says my velocity is 40 miles an hour and my speed is 40 miles an hour. Don't you think they're just telling me the same thing? Right? Technically, they're not. Velocity has a direction associated to it. So if you do any physics class, can't you go at a velocity of minus 10 miles per hour? You can have negative velocities. So just get used to that distinguishing feature. Now, if you wanted to know the velocity vector, the acceleration vector, or the speed at any given time, don't you just put in the value of t and you've got it. So suppose this was our moving object, right? And I wanted to know all those things when t equals 1. Well, the velocity at 1 would be 2 times 1 e to the 1, 2. The acceleration at the 1 second mark would be 2 e 0. The speed at the 1 second mark would be the magnitude of the velocity vector, which would be the square root of 4 plus e squared plus 4, and that would be the square root of 8 plus e squared. So can't you find velocities, acceleration vectors, or speed at any given value of t that you possibly could want? In fact, if I wanted to do a formula for speed, right? So instead of having to find this vector's magnitude every time, wouldn't I just take this guy and find the magnitude of that vector? And that would be the square root of 2t squared plus et squared plus 2, and that would be my formula. Speed is always positive. So if you ever come up with speed and you think it's a negative number, check your calculations. It ain't going to happen. So far, so good. Any problems? Seems reasonable. Right, so you're going to find derivatives. They're going to tell you velocities, accelerations, and cool stuff like that. So I'm looking at the first question. Should be a nice, easy one. Here is my space curve. It's given in the IJK notation, which you all know I don't like. Right, and we're being asked to find velocity, acceleration. So let's do the velocity first. We now know that's the same thing as the first derivative. So it's 1, 2t, 0. You want the acceleration? Well, we know that's the second derivative. So we differentiate this and you get 0, 2, 0. They don't call it the speed, but I will. They call it the magnitude of the velocity vector. So they're basically telling you how to calculate it, but I would call that the speed. And the speed in this case is the square root of that guy, right? Square root of him. So it's 1 squared plus 2t squared plus 0 squared. And that's 1 plus 4t squared. And that is the answer. No, it's not 1 plus 2t, which even till this day, some of my students still think is a good answer. Square roots cannot be simplified when there's a plus in the middle, right? If it was 4t squared, couldn't you simplify it and call it 2t? Right? But 1 plus 4t squared, all bets are off. So that's the final answer. You can't fix it. It's done. And they go in and they ask you to do graphs of things, but won't you just go to your Desmos thing and, you know, your GeoBra, I should say, and put it in and look at it? And there'd be 4 pictures and one of them would look like that. And if they ask you for the velocity one, it would be that. Okay, that one looks. Yeah, let's do this one. This is question 3. I'm picking this one for style points. I'm picking this one because you can simplify the square root. So it's going to be 8 root t, yikes, t, e to the 8t, which is okay, and e to the negative 8t, which is okay. And we'll find the velocity vector first. It's the first derivative. That guy gets you 8 root t, root 2 I should say. This guy gets you 8 e to the 8t, and the derivative of this one, negative 8 e to the negative 8t. You go with that for velocity? Pretty much plug and chug right now. If you want the acceleration, just find the second derivative. Derivative of a number is 0. This one gets you another 8. And this one gets you a 64. Comfortable with that one? Right. So I wish they would call it speed. I'm still going to call it speed. But they ask you for the magnitude of the velocity vector. And that is going to be the square root of this guy squared plus this guy squared plus this guy squared. And 8 root 2 times 8 root 2 is 64 times 2, so 128. 64 e to the 16t and 64 e to the negative 16t. Are we cool with those calculations? 64 times 2, 64 is this guy, 64 is this guy. And this one, this guy here, can be simplified. I'm going to take it really slow so I don't make a mistake, I hope. Style points means make the answer pretty. Okay. Open to suggestions. Inside that square root, is there anything you can do? Even a little thing will help.
You can combine the e terms into just 64 e to the 1.
If you were multiplying them, you might be able to do that, but not as an addition.
Oh.
Okay, but it's good. You're thinking. I like thinking. Anything else? Okay, let's do that. If you pull out 64 as a common factor. Now I'm going to end up doing probably a lot more lines than you might choose to do if you were doing it, but if I do it slowly, it will make it easier for others. Now, when you have a square root and two things are multiplied, you're allowed to simplify them in a way that you couldn't if they were just added. So this is going to be the square root of 64, which gets me 8, and I'm going to leave that guy alone. Are you comfortable with what I just did there? Right? It's looking nicer. But if you see
a perfect square,
you beat me to it. Exactly, David. I was about to say that when you see a square root with 3 things in it, isn't there a fairly good chance it's going to be a perfect square? And the answer is yes, this one is. So remember arc length when we had square roots, which were quite ugly, but if you got lucky, there was a perfect square inside the square root. So we need to figure out my red pen. How could I lose it? Okay, got it over here. This guy here is going to contribute to the term that goes here. And this guy here is going to contribute to the second term that goes here. Okay, any suggestions? What does e to the 16t get you when you do this process of completing the square?
e to the 8t.
Right, you halve the power, which is essentially square roots. And the same thing here. Can you trust me, if you FOIL that out, it works perfectly. Agreed?
I have a question.
Yes.
Could you have done that before you took the 64 out?
Yeah, you would call that 8e to the 8e to the 8t, and 8e to the negative 8t. Yes. Yeah,
Would
it's a short
that
answer.
be correct?
Yes, would be
Ah.
correct.
Thank you.
And this now becomes 8. The square and the square root all cancel, and you got your answer. Now, if you did it the other way, you would have to have then just pulled out an 8 as a common factor. So you still would have pulled it out. I pulled it out at the start, and you could have pulled it out at the end. So if Dylan was saying, could we have just started here and went into it, you would have been able to do that. The answer you got wouldn't be this, but the next line it would be this. So yeah, you save a line and it might be easier to deal with. Right. We cool? Perfect square. If it's not a perfect square, well, that's it. You just write it down and leave it alone because there's nothing else to be done. Are we good with questions then that just ask you for velocity, acceleration, and speed? You feel comfortable with them? Right. Good. So let's work backwards. Can you remember in Calc 2 where somebody might have said the velocity is that, find the original function? Can you remember doing those? Didn't you have to integrate this to get that? We're going to do the same thing now. So the question that I'm picking is number 5. And we are being told the acceleration vector, and it's 2, 0, 2t. And we're also going to be told that the velocity at time 0, the velocity vector, is 9, -1, 0. And that the position vector, the space curve, at 0 is 0, 1, 1. These are like boundary conditions. These two things are what's going to get me. And well, if I did this one, the answer would be 1/3 t cubed plus 3t add c, right? And then wouldn't you be told something like the position at 0 was 10, and that would allow you to find the c? Can you remember that part of the puzzle where they gave you something? We call them boundary conditions, right? They told you one specific value of the function, and its job was to get you c. So that's what these guys are. This is just a kind of grown up, bigger version of that world, right? So I'm going to start then with taking this guy and finding the velocity vector. Well, that's going to be the integral of the acceleration vector. And if you want to integrate a vector, right, like here, don't you just integrate separately? So you're going to find the integral of 2, the integral of 0, and the integral of 2t. And if you integrate this guy, you get 2t plus an unknown constant. If you integrate 0, you get 0 plus an unknown constant. And if you integrate 2t, you get t squared plus an unknown constant. So far, so good. But these right now aren't strictly speaking correct. Because what I've written down mathematically is that this unknown constant is the same number each time, right? But couldn't this be 4, 2, and 59? Couldn't they each be different? And so you have to distinguish them. That's going to be called C1, that's going to be called C2, and that one's going to be called C3. So we still have an arbitrary constant, but don't we have a unique one for each of the 3 components? Does that make sense that you would need to do that? Otherwise, you'd be making an assumption that really isn't valid. Now I'm going to use this piece of information to figure out who these guys are. So if you tell me the velocity at 0 is 9, -1, 0, right? So this is the velocity at t. But if you tell me the velocity at 0 is, put it here, is 9, -1, 0. If I put 0 in here, I get nothing plus C1, nothing plus C2, and nothing plus C3. And can you see I can now match them? And there's no reason why these numbers are always going to be C1, C2, and C3. Can you imagine that sometimes you have to add one or take away one or something, right? But in this case, C1 is 9, C2 would have to be -1, and C3 would be 0. So now I know everything about the velocity function. It's 2t plus 9, it's 0 minus 1, and it's nothing 0, so it's just t squared. Are you comfortable about how we found C1 and C2 and C3 by using this boundary condition? I really wish they hadn't picked 0 here, because people are just going to think the numbers there are always going to be here, here, and here. Side issue, just pretend for a minute that one of these things was actually e to the t plus c1, right? Just for argument's sake. And the velocity at 0 was 9, right? When you do a matchup with e to the 0, don't you get e to the 0 plus c1? Don't you get 1 plus c1? And that equals that makes c1 8. So what I'm trying to say is, don't get into the habit of thinking, oh, well, they just mean C1, C2, and C3. You see, they don't always do that, right? Even in this case, they did. Right. Now find acceleration. Well, I just need to integrate the velocity. Oh, wrong direction. I need to find position function. So I integrate the velocity function. T squared plus 9t plus an unknown constant, -t plus an unknown constant, and 1/3 t cubed plus an unknown constant. And then I can use that guy to find out who C1, C2, and C3 is. Unfortunately, again, can you see that's going to be C1, that's going to be C2, and that's going to be C3, right? Can I just do it in my head? You can see it's going to work, because wouldn't that just become nothing plus C1, nothing plus C2, and nothing plus C3? So next question I'm picking, it's not going to be zeros everywhere. So we have a t squared plus a 9t plus 0. Guess I don't write anything there. A -t plus a 1. And a 1/3 t cubed plus a 1. Are we good about integrating to get velocity, integrate velocity to get position, use these boundary values to find the arbitrary constants C1, 2, and 3? Right. I'm going to make one of my own up so that we don't have that annoying feature that these just be the constants. So here's mine. E to the t t squared 5. And start with the acceleration vector. And I'm also going to tell you that the velocity at 0 is 2, 1, 4. Right, so the velocity is the integral of the acceleration vector. In this case, you get e to the t plus an unknown constant, 1/3 t cubed plus an unknown constant, 5t plus an unknown constant. So there's your velocity vector. The velocity of 0 is this guy. So if I find the velocity at 0 using this formula, e to the nothing gets you 1 plus c1. That guy gets you c2, and that guy gets you nothing plus c3. And we know that the velocity vector at 0 is also 2, 1, and 4. Now, when we do the matchup, isn't C3 going to be 4? You do this matchup, C2 is going to be 1. But when you do this matchup, what is the value of C1? Because it's not 2.
1.
1. You see what I was getting at? That you don't just say C1, C2, C3 and don't think about it. You see, sometimes you have to work on it, right? It's not always going to be the guy you think it is. Now you put that together then. The completed velocity function is e to the t plus 1, 1/3 t cubed plus 1, and 5t plus 4. Are we comfortable with that process? Now, if I wanted to find, which I don't in this question, but if I wanted to find the position vector, couldn't I simply just integrate this all with a C1, a C2, and a C3, and then boundary value would identify what numbers these would be. So it is a nice process. Yes, question.
Wouldn't C1 be 2 plus 1, so 3?
Well, let's check it out. This guy has to equal 2.
Oh, it has to equal 2. Okay,
Yes.
I see.
So it's
never mind.
not, yeah, I'm not combining them. I'm saying the first thing is the same as the second, right? So I'm saying they're equal to each other. Right. That's what we're saying. Any other questions? We're good. We shall pick. Okay. This one is question 7. Acceleration vector is 19 ti plus e to the t j plus e to the negative t k. If you hear growling, it's my puppy wanting attention. V of 0 is equal to k, and position space curve at 0 is equal to j plus k. I thought I'd write down all those ij's and k's to try and tell you why I don't like ij's and k's. And you can choose to work with them, and I'm totally cool with that because not everyone's the same as me. That's what this becomes. This one here becomes 0, 0, 1. And this one here becomes 0, 1, and 1. Now, in my brain, that's just the same information, but just more obvious to me. You know how careless I am? Can you imagine how bad I am when there are I's and J's floating around? Because isn't it dead easy to think an I's a J and you put it in the wrong space or you match something or whatever. So I know if I'm trying to sell you this notation, I'm just saying I like it, right? So let's work backwards then. I'll find the velocity, which is the integral of the acceleration vector. If you integrate this guy, you get 19 halves t squared plus an unknown constant. Then you get e to the t plus an unknown constant, and negative e to the negative t plus an unknown constant. Are we okay with that? Everything look good? Right, okay. If I find the value at 0. Oh, by the way, there is no reason in the world why you need to know v of 0. Wouldn't this work equally with v of 1 or v of 22, right? You know, there's no particular reason why it should be 0. It just happens to be that 0 is a good number. So if you plug it in here, you get C1. If you plug it in here, you get 1 plus C2. And if you plug it in here, you get negative 1 plus C3. So I've just replaced the t with 0, and now I have this guy. If I write down right underneath it what the boundary value is, the boundary value is 0, 0, 1. And then you match them by making them equal to each other and seeing what the value for C1, C2, and C3 would be in each circumstance. Okay. If this guy is going to equal this guy, would you agree C1 happens to be 0? Right. If you make this one equal to that, what is C2 going to be?
Negative
Negative
1.
one.
Negative 1. And lastly, if you match this one with that one, what will the value of C3 end up being? If this, okay. And if you put this package together, then the velocity vector is this guy plus nothing. So that's 19 halves t squared plus C1, which is 0. The middle one is e to the t minus 1. And the end one is negative e to the negative t plus 2. And there is our velocity vector. This is quite mechanical, isn't it? Once you've done a couple of them, you've done all of them, right? I can do it if you want, but I don't want to if I can get away with it. Couldn't I then move on from velocity vector to position vector and then use this guy to figure out who the constants are? So I would just integrate each of these and then match them up. Can we just say ... You could do that yourself. And then they've got some picturey thing if you want to look at it. The last thing, well, actually, we'll be doing it tomorrow, but at least it gives me a reminder to do it tomorrow. We're going to find the tangential and normal components of acceleration. Imagine that you find the acceleration vector, right? So you started off with your space curve, right? And you found the second derivative, and that was your acceleration vector. A fascinating property is that the acceleration vector is always a linear combination of the tangential, right, the unit tangent vector, and the unit normal vector. And that's a number, and that's a number. Well, it depends on the vector position, right? And this guy is called a little t, and this guy is called a little n. And a little t is its name is the tangential component of acceleration, and AN is called the normal component of acceleration. Now, can you remember when we did the shooting off to your death guy, right? That guy there, the unit tangent vector, wasn't it the direction you shoot off to your death, but we made the vector 1 unit long. Remember that guy? And there was another vector called the unit normal. Remember, the unit normal went this way and is at right angles, and it was that kind of curvy force that pushes you like you're going round a corner, right? And that's a unit vector as well. The acceleration vector is essentially a combination of these two, which intuitively doesn't make sense to me, but I'm not a physicist. But evidently, the acceleration vector is basically just made out of a combination of these two vectors. Why are they quite useful? If you are doing an object traveling in 3D space, like a spaceship, and would you agree it's quite difficult to decide where the origin is? Secondly, don't things keep moving in 3D space? Like the Earth isn't going to be where it is right now in 2 seconds from now, right? Won't it have shifted? Technically, you might think, well, the sun is fixed. Well, the sun is not fixed. You know, the sun is part of the Milky Way and it's going round a spiral. So the sun's moving. Well, how about the center of the galaxy? No good. Galaxies are moving. What about the universe? No good. The universe is moving, right? It's expanding. So there isn't a point in space that stays put for your origin, right? So how do they get around the idea of how do you locate yourself in 3D space when you don't have a central point to say, I'm this far away from here, right? Because here keeps moving, right? So the workaround that they do is that they use the unit tangent and the unit normal like your X and Y axes. And remember that one, we've never even bothered to calculate the unit binormal. Don't you have an X, Y, and Z axis, man? Can't you make the unit tangent your X, the unit Y, the unit normal your Y, and the binormal your Z? Can't you use those? And at any given point in time, won't those three always be right angle to you? So you can always at least tell where you're going in relation to these three vectors. So it's a way of trying to avoid the fact there's no up in space and there's no origin in space.